Good day to all of you. Welcome to Prim's algorithm part 2. In part 1 video I have covered what is Prim's algorithm, what are the steps involved in it, and we have solved one problem on Prim's algorithm. In today's session we shall solve one more problem on Prim's algorithm, but writing of steps is little bit different, but that will help to follow the C program on Prim's algorithm very easily. Let's start the session. Today we shall solve this example 2. The problem statement is find the minimum cost spanning tree using Prim's method with greedy approach for the graph given below. That is this graph with A as the arbitrary root. So from A vertex we have to start the procedure. This is the original graph given and it is copied here for marking the subgraph, that is minimum cost spanning tree. That is first point. Next, if you observe this given original graph, number of vertices is 7. So 1, 2, 3, 4, 5, 6, 7. These are the 7 vertices. Number of edges is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this original graph has vertices equal to 7 and number of edges equal to 9. That is second point. So when we find minimum cost spanning tree subgraph in this, it will have same number of vertices, that is 7, but the number of edges will be 6, that is 7 minus 1 equal to 6. Number of edges in original graph is 9. Number of edge in minimum cost spanning tree subgraph will be 6, that is less. That means minimum cost spanning tree subgraph will have only those edges which will be connecting all the vertices in the graph but still maintain sum of edge weights as minimum. That is what is minimum cost spanning tree subgraph. Okay. Now we shall find the minimum cost spanning tree for this original graph. Means for all the vertices present here, we shall mark the edges which are required according to Prim's procedure. Okay. So here in the table A to G, these vertices are marked as column names. Then we are starting with vertex A, which is mentioned in the problem statement. For all the vertices, the weight is marked as infinity. Only for starting vertex, it is taken as 0. This is the start point. So for A vertex from where we have to start, the weight is written as 0. For all other vertices, it is written as infinity. This is the first point. This you have to remember in the C program also. This is done in initialization part. Okay. Now for this starting vertex, this is the starting vertex, which are the adjacent vertices, means connected vertices. So this F vertex and B vertex are the adjacent vertices because they are connected with these edges of weight 10 and 28 respectively. So in the table also we will write this. A vertex is connected to B vertex with an edge having weight 28 and F vertex with an weight 10, which is present here. Okay. Now we'll mark these two with green colors. So out of these two, 10 is the minimum. So after that we are marking this 10 which is minimum with blue color, right? This color scheme just I am explaining as to follow the steps easily. Okay. So now what this indicates? Vertex A is connected to B with the weight of 28. Vertex A is connected to B with the weight of 28. Vertex A is also connected to F vertex with the weight of 10. Vertex A is also connected to vertex F with the weight of 10. And out of these two, 10 is the minimum. So 10 is the minimum which is connected to F vertex. Okay. Hence F vertex is added to minimum cost spanning tree vertices array. So for which are there? A is there, F is there. So A and F vertices are connected. This 10 weight is marked for vertex F, means F vertex is marked with weight of 10. Still all other vertices will be having the weight infinity. This is an important observation. So whatever steps we followed now for A vertex, now we will have to follow for F vertex. So what are the steps? For F vertex, first we have to identify which are the adjacent vertices. Then note down the weights of all connected edges. Which is the minimum? Choose that vertex. We have to add that vertex to this minimum cost spanning tree vertices array. Then we'll have to mark that minimum weight on the chosen vertex and maintaining all other vertices weights as infinity. So these steps we have to continue, right? These steps understanding is very important to follow C program on Prim's algorithm. Okay. So for having clarity in steps, I have marked the steps with color code. Okay. Here. Next for F vertex, only one edge is there which is connecting with E vertex. So E vertex is connected to F vertex with a weight of 25. That is the only one edge. So one important point in Prim's algorithm is whatever vertices are present in minimum cost spanning tree vertices array. So here A and F are there. From those vertices outgoing edges we have to consider. So this 25 weight edge which is outgoing from F and connected to E. So that is why it is marked with green. And another one edge with weight 28 from A it is outgoing. So it is connected to B. So that also we are marking with green. Now these two are to be compared, which is the minimum. So in minimum cost spanning tree vertices array A and F are there. From A outgoing edge is this which is connected to B and the weight is 28. And from F vertex the outgoing edge is this which is connected to E and the weight is 25. And out of these two, that is green marked here, that is, so out of these two, 25 is the minimum, so it is marked with blue color. Because this weight is minimum, it is connected to E, this E that is added to minimum cost spanning tree vertices array. So this F to E is connected. E vertex will be marked with weight of 25. So E vertex will be marked with weight of 25. And all remaining vertices will be having still the weights infinity. So till here another step is completed. Means whatever steps had done for A, now it is completed for vertex F. Next we'll have to repeat the same steps for vertex E. Okay. What is the status of steps so far? The status is in minimum cost spanning tree vertices array, A vertex, F vertex and E vertices are there. They are connected. So A vertex is connected to F vertex is connected to E with the A weight of 10 which is marked here and with the weight of 25 which is marked here. So these two, right? A to F is connected and F is assigned with weight of 10. F to E is connected and E is assigned with weight of 25 and all other vertices still will be having weight as infinity. So this is the status so far. Okay. Is the procedure ended? No, because in the minimum cost spanning tree subgraph finally we'll have to have 6 edges. We have only 2 edges. So procedure is not yet completed. We have to continue with vertex E now. Whatever procedure we did for A and F, now we'll have to do for vertex E. Okay. Next, taking E vertex, it is connected to two vertices G and D. They are the adjacent vertices. So here the edges are with weight 22 and 24. They are written here. So the outgoing edges from these vertices are from A, it is 28. This is not considered already covered. So 28 is present, that we have to take into account. Then from F, so this is already covered. So that is why it is marked. We will not consider this. Then from E, there are two edges. So they are marked with green. So the latest outgoing edges 22 and 10, 24, and the old one is 28. Out of these three, 1, 2 and 3. So these two and this one. 22 is the minimum. So the 22 minimum weight is connected to vertex D. So 22 minimum weight is connected to vertex D. Hence, D is added to minimum cost spanning tree vertices array and E to D is connected. So, and this 22 weight is marked. Means for vertex D, so for vertex D, the weight is 22, that is added. Okay. So far the status is for F the weight is 10 and for E the weight is 25 and for D the weight is 22. So they are marked with red colors here. So far the status of solution is A to F is to be connected. So A to F is connected, F to E. So F to E, E to D, E to D is connected. That is first one. Then we started from A vertex, so weight is 0. For F vertex it was found to be 10. Then for E vertex it is 25 and for D vertex it is 22. So this 10, 25 and 22, they are underlined with red color here. So what is not underlined is 28. So this one. So this edge is not yet connected. It is not used for connecting because its weight is more. Okay. Now from D, there are two edges connected to vertices G and C with weights 18 and 12 respectively, which are written in the table here. Now the weights to be compared are this 12, this 18 and previous which is not connected 24 and 28. If you cross verify from vertices in MST vertices array, the outgoing edge from D are, there are two. So these two are to be compared, and from E, there is one outgoing edge, so that is 24. So this has to be compared. So from F there is no outgoing edge, the two are already considered. Then from A, so from A 28 is there which is not considered. So we have totally 4 outgoing edges from this, that is 1, 2, 3, 4. Among these 12 is the minimum. So this 12 is the minimum. So 12 is connected to C vertex. So 12 is connected to C vertex from D vertex. So C vertex is added to MST vertices array and D to C is connected and 12 is marked here and weight for C vertex is 12 now. So for A it was 0, for F it is 10, for E vertex 25, for D vertex 22 and for C vertex it is 12. So they are marked with red here. So 10, 25, 22 and 12. So according to these red color marking, A is having weight 0, F is having weight 10, E is having weight 25, D is having weight 22 and C is having weight 12. So remaining still as per initialization they will be having infinity. that way highest weight. And for the next step, outgoing edges to be considered from previous step are this 28, 24 and 18. So we'll have to repeat the procedure for C vertex now. Okay. For C vertex, only one adjacent vertex is there. So it is connected with the weight 16. So for C vertex, so B vertex is connected with the weight 16, that is written in the table here. Next weights to be compared are 16, then 18, this 24 and 28. So these are the four outgoing edges if you verify from the vertices in the MST vertices array. So among these, 16 is the minimum. So 16 is marked here. Okay. And that is connecting C to B. So C to B. So B is added to MST vertices array. C to B is connected. And this 16 is marked. So weight 16 is assigned to vertex B. So B is connected to A vertex and G vertex with weights 28 and 14. So B is connected to A vertex with weight 28 and G vertex with weight 14. Next weights to be compared are 28, 14, 18, 24 and 28. So if you verify, these will be the outgoing edges from the vertices in the MST vertices array. So this 28 is here, this 14 is here, this 18 is present here, this 24 here. So this 14 is the minimum. This 28 is not considered because if you consider this, it will form the cycle. So either this 28 or this 28, A to B or B to A. So this will not be considered. If it were less also, around 7, 5, so lesser than these, then also it cannot be considered because it forms the cycle. This is a very important point. So 14 is marked. This 14 is connecting B to G. Hence this G is added to MST vertices array. B to G is connected. Now what is the next step? If you consider the MST subgraph here, minimum cost spanning tree subgraph. This is the original graph and we have found the subgraph here. At this status, if you observe the subgraph, 1, 2, 3, 4, 5, 6. 6 edges are there. So we have to stop the procedure. So when any original graph is given with Prim's method, with greedy approach, if we find the MST subgraph, number of vertices will be same as original graph, but number of edges will be one less. So if 7 vertices are here, here also 7. And number of edges here already 6. Hence we will have to stop the procedure. Okay, the solution is completed. So minimum cost of this subgraph is, we have to add all these connecting edge weights. So 10 plus 25 plus 22 plus 12 plus 16 plus 14, that is written here, that comes out to be 99, and that is the end of complete solution. Okay. So we started from this original graph in that A vertex here, the weight was assigned 0. As we progressed here, the weight is 10, here 25, here 22, here 12, here 16, and the last one is 14. So in this sequence, when the edges are connected, which is specified in the MST vertices array also, A to F, F to E, E to D, D to C, C to B, C to G. So the sum of all those weights is 99. So that completes the solution. So in today's discussion, what I suggest is, you once again go through all the steps whatever have been followed here according to the algorithmic steps for Prim's algorithm. with greedy approach, which already we have seen in last video. That only we have followed. Way of writing is different. With what notations we explain whole procedure, you once again go through that. So those steps are very important for following the C program for Prim's method. So there one function to represent this graph will be used, another function to find the minimum weight. So one more function to find the MST graph, one more function to print the found MST graph, one array to store all the vertices in MST vertices array, another one to mark as we progress through the solution which weights are to be assigned for every vertex in respective steps, and indices of matrices like U and V. So A to F, A to B means U is A here, V once it is F, V another time it is B. So U and V, though these indices we must be able to follow. Next, weight of V is assigned 10. If V is F, weight of F assigned is 10. So that is weight of V. V is the index, that equal to 10. Such statements we come across C program. So that we must be able to follow. That we can follow when we thoroughly study these steps. So please once again or many times go through the steps, and then you can move on to C program for Prim's algorithm. Okay. I hope you have understood. Thank you.